First talk is by Alexandre Zvonkine, and we will talk about value functions.
Thank you. Value function is the main notion of this course. It makes sense for the complex sphere, but also for the Riemann surfaces of arbitrary genus. But for the planar case, it is much simpler, so I will start. And for today, I will touch only the planar case. Belly is the name of a Russian mathematician, and in fact, he wrote a paper on Galois theory of about 20 pages, at which there was an appendix of 1/3 of a page at the end of his paper. And in this appendix, he wrote something which later on explodes in the whole thing. So I will start with some technical remarks. The first remark is that coefficients of polynomials are simpler than their roots. It is a triviality, but it would be better to say it. So, for example, this expression, which I should in fact write in the way x minus this thing times x minus this thing times x minus this thing, and so on. But there was not enough place in the line. So this long expression, which goes from here to here, is much more complicated than this one. Okay, so whenever possible, I will collect several points, several roots of polynomials in a single polynomial in order to simplify the fields in question, the coefficients in question. Now, the technical remark, kind of a longer one. Suppose we have a polynomial p which is decomposed like that: p1 to the degree d1, p2 to the degree d2, and so on. The degrees are different, distinct. Polynomials p are coprime, and the coefficients of the polynomial p belongs to some field. Then the coefficients of polynomials p1, p2, and so on, pk, belong to the same field. So I do not spoil the field if I consider these polynomials p1, p2, p3 separately. The proof is rather simple. So first of all, I compute the derivative. Its coefficients belong to the same field. Then I compute the greatest common divisor of polynomial and its derivative. It is not equal but proportional to this product of the same polynomials, but the degree are smaller. Then I divide p by this thing and get the all the polynomials only once. Then I divide what I compute a, which is p divided by this product to the degree dk. Then pk disappear. Okay, I obtain the product of polynomials up to k minus 1. I divide, and in this way I obtain pk by making the operations only with coefficients belonging to the same field k. So this is a purely technical remark which I will need in order to represent the functions I will look for. So before giving a formal definition, I will consider in some length an example. So we have a map with 10 edges, and I will look for a rational function of degree 10. Usual rational function, polynomial divided by polynomial. And I impose many conditions of this function. So first of all, okay, it must satisfy the following conditions. The first one, the black vertices are the roots of this function, and the multiplicities of these roots are equal to the degrees of the black vertices. So the numerator of our rational function, it is of degree 10, okay, but it has only 3 roots because there are 3 black vertices. One root is of multiplicity 6, one root of multiplicity 3, and one root of multiplicity 1. So the numerator must be of this form. It is not equal, it is proportional up to a constant. Now, the second condition. The white vertices are the roots of f minus 1. Or if you prefer, the white vertices are solutions of the equation. The black vertices were solutions of the equation f equal to 0. Now I consider the equation f equal to 1. Or you may say the same thing. Black vertices are pre-images of 0, white vertices are pre-images of 1. So there are 3 white vertices of degree 2, here, and here. And I collect them in one cubic polynomial. So these points are roots of this cubic polynomial to degree 2. Recall my idea of collecting the roots in a single polynomial. Okay, and there are 4 vertices, 4 white vertices of degree 1. 1, 2, 3, 4, and I collect them, so they are 4 roots of this polynomial of degree 4. Well, the next condition, there are many of them. Inside each face, there is a single pole of our rational function, and the multiplicity of the pole is equal to the degree of the face. So there are 2 faces, this one and the outer one. Therefore, my function should have 2 poles. These poles are roots of this quadratic equation. And, okay, this must be verified, but the degrees of the faces are both equal to 5, and therefore my quadratic polynomial should be taken to the degree 5. So finally, if I consider 3 equations, f equal to 1, f equal to 0, f equal to 1, and f equal to infinity, these equations have multiple roots. So the next condition, which is in fact is not a condition but a consequence, but it is necessary to say, there is no other critical values except these 3 ones, except 0, 1, and infinity. I ask you to distinguish between critical points and critical values. Critical points are the roots, which might be multiple or simple. Critical values are the values of the function at these roots. Okay. So there are only 3 critical values, but critical points are vertices and some black vertices, some white vertices, face centers, and so on. So we will see that in this case the map itself can be obtained as the pre-image of the segment 0, 1, when 0 is colored by black and 1 by white. So finally, what do we have? F of x should have this form, numerator, denominator. You remember this numerator, power 6 and 1, denominator, and f of x minus 1 is like that. Well, the constant term, the constant factor is just computed. So cubic polynomial to degree 2 because there are 3 white vertices of degree 2. Polynomial of degree 4 because there are 4 white vertices of degree 1, and 2 faces which are roots of the centers, the poles are roots of this polynomial, both to degree 5. Okay, so we just equate these two expressions. So we may compute f minus 1 and impose the condition that it should look like that, which gives us the leading coefficient is in a way fixed. So this gives us 10 equations for 13 parameters. And it is a general phenomenon. There are always 3 more variables than 3 more parameters than the number of equations. This represents, this situation represents the possibility to act on x by a fractional linear transformation. So, making a fractional linear transformation, we can put, for example, it is not the only possibility, but for example, we may take a equal to 0, b equal to 1, and c equal to minus 1, for example. And then, to solve the system of the algebraic equations, which is not easy at all. And here is what we get. So you see x to the power 6, it corresponds to this point. X minus 1 to cube, it corresponds to this point. X plus 1, so minus 1 is the position of this point. And if we consider f of x minus 1, there are three double roots, they are here, and 4 simple roots. Okay, one of them just went away from this polynomial, it is by chance. And the poles are 2 roots of this equation. Finally, we may take the pre-image of the segment 0, 1 and obtain this map, but in some specific geometric form. Here, black vertices are denoted by little squares. So, white ones, black ones, and so on. Well, in fact, the situation is rather more complicated. First of all, I didn't explain how I solve this system of equations. If I try to solve it directly, it will be too hard. So there are some computational shortcuts. For example, it is more interesting to equate derivatives because the derivative of f and derivative of f minus 1 should be equal. And okay, so I will not dwell on this topic. The much more difficult situation, well, there is additional difficulty is that in fact what should I add to the corresponding system of algebraic equations is the condition that all the roots of my polynomials are distinct. And when I just solve this system, it produces many parasitic solutions when some roots coincide. For example, one of the solutions is that here we have x to the power 6, and here we also have x to the power 5 and another x. And x to the power 5 disappear, and we get something of degree 5 instead of degree 10, and so on. But there are more profound complications. In fact, when I wrote the equations, the only information I used is the information about the degrees of the black and white vertices and faces. I didn't use any other thing. But there is not one, but 7 different maps with this set of degrees. Just look, for example, here. Black vertices of degree 6, 3, 1. White vertices of degrees 2, 2, 2, and 4 times 1. Or this one, for example, or this one. 6, 3, 1, and 2, 2, 2, and so on. So 7 different maps with the same set of degrees. The terminology we use often is passport. 7 pictures with the same passport. Okay. And all I need to find out that there are exactly 7, not less, not more. It is not an easy thing to do. So I don't know how to do it in an efficient way. And I propose to the audience the following question. Forget about white vertices, consider usual maps. So there are white vertices, but all of them are of degree 2. So we have just usual maps with only black vertices and edges which go from black to black. Okay, maps with 6 edges with vertices of degrees 6, 3, 1, 6, 3, 2, 1, and faces of degrees 6, 3, 2, 1. So my proposition is to find a complete list of these maps. Whoever will do it not after several tries, but from the first try, and get a correct answer, will get a bottle of Bordeaux.
Which one? Which one?
Chateau Petrus. Of course, for 6 edges, it is quite possible just to make an exhaustive enumeration of all maps with 6 edges and choose better ones. But for bigger number of edges, I don't know how to approach this problem. I don't have any efficient algorithm to do that. What I can do is to compute their number, which is sometimes not easy either, but using the character tables of symmetric groups, or even for other groups, this computation is possible. Well, so there is, well, among these 7 maps, for this one, I will give also the corresponding Bernoulli function. Here it is. You see that the numerator is the same, but the denominator is different. Well, and f of x minus 1 is a rather long expression. So one of the questions is I have two Billy functions. How do I distinguish between the corresponding maps? I mean, how do I find which function corresponds to which map? In planar case, I can just compute. I make a picture and I look at the picture and it is done. When I have to do with surfaces of bigger genera, I cannot draw efficiently. Not efficiently. I cannot make pictures. So the problem becomes not trivial. And even when I make a picture, okay, I see, my eye sees what is the map. But in fact, it is not a rigorous statement. What we see here are not lines, but just isolated points. We see them as lines, but they are, strictly mathematically speaking, there are 100 points, the pre-images of 100 points on the segment 0, 1. So, to prove that it is convincing but not rigorous, my way of determining which map it is. Now, for the remaining 5 maps, the situation is even more difficult. And here we see for the first time a Galois orbit. What do I mean by that? The coefficients of our rational functions belong to the splitting field of this polynomial of degree 5. So I take a Billy function for one map. I replace simultaneously all the coefficients by their algebraically conjugate, and I get another map of this family, of this Galois orbit. I make this operation once again, and I get a third map, and then fourth, and then fifth. Okay, so the coefficients belong. The coefficients depend on some parameter t, which takes 5 values, which are 5 roots of this equation of degree 5, and taking one by one these roots of the equation of degree 5, I get my 5 maps. Okay, so the concrete polynomial we see here may depend on computation, on the computation procedure. We may get a different polynomial, but the field is objective. I mean, we can get a different polynomial of degree 5, but the splitting field will be the same. And it is not, here we touch every, wherever we look, we touch a difficult problem, a non-trivial problem. For example, if there are 2 quadratic equations, it is very easy to see if they generate the same field. We just take the square root of the discriminant, and if it is the same square root, then it is okay. Already for cubic equations, it is not at all an easy question. We have 3 cubic equations. The roots generate 2 cubic fields, 2 cubic extensions of rational numbers. How to determine if it is the same field or not? there are algorithms, there are answers to this question, but they are not trivial at all. Well, one more question. I chose the position of this point at 0, at 1, minus 1. This was my choice, but why didn't I take one pole at 0 and the other pole at infinity to get a Laurent polynomial? It would be probably more interesting to get a Laurent polynomial. In fact, what we were looking for was indeed a Laurent polynomial. This is not a random example. We have a paper of 3 authors, two my co-authors and myself, dedicated explicitly to this Dessin. Because it is an example of Laurent polynomial. There is a polynomial moment problem and some phenomena which do not occur with usual polynomials may occur with Laurent polynomials, and this is the first known example. When the set of the space of polynomials orthogonal to all degrees of a given polynomial are much larger than usual. So okay, if I try to put one of the poles to 0 and the other one to infinity, I just have to make the corresponding substitution. The fractional linear transformation, and I do get a Laurent polynomial. So you see, here is z to the degree 5. The degree of the numerator is 10, so there is one pole at infinity of degree 5. But the coefficients now belong to bigger field, to the field q of square root of 5, which rather spoils the answer, since if we replace square root of 5 by minus square root of 5, we get the same map, but turned inside out. The inner and outer face exchange their positions. So it is an action of Galois group which does not change our map. So it is a kind of inconvenience in this computing. So finally, general theorem. For any bicolored plane map, such a function exists. A function which has only 3 critical values, 0, 1, and infinity. Black vertices are pre-images of 0 with multiplicities they must have. White vertices are pre-images of 1 with multiplicities that must have. In each face there is a single pole with the multiplicity equal to the degree of the face, and there are no other critical values. Okay, there is some liberty of making fractional linear transformation. The coefficients can be made algebraic numbers. It is a rather cautious formulation, because if I were stupid, I could make, instead of 0, for example, to take pi, and instead of 1 to take square root of e, or something very crazy, or a zeta function of 3. So I may get my coefficients as absolutely crazy numbers, but it is always possible to get them as algebraic numbers. And then there is a famous absolute Galois group, which is the group of automorphisms of the field of algebraic numbers. People usually write here Q. Q is fixed by this group. Okay, so if we take a Belly function whose coefficients are algebraic numbers and act on this function, act on coefficients by an automorphism of the field of algebraic numbers, we get another Belly function. This can be proved. And therefore we get another picture, another Dessin, another map. Therefore, this group, the group of the Galois group, acts on maps, which was very unusual, which was very surprising at the time. So the map itself is the preimage of the segment 0, 1. It is the simplest possible map. One edge, one black vertex of degree 1, one white vertex of degree 1, and the outer face, the single face of degree 1. So every map is a preimage of this simplest possible map. And the cartographic group generated by our three permutations is the monodromy group of the corresponding covering. And it is, by the way, an invariant of the Galois action. So if I return to one of my pictures, the cartographic group here is isomorphic. It is a group of degree 10, acts on 10 edges, but it is isomorphic to S5. This one is isomorphic to S6. And for these 5 maps, the group is just S10. Okay, so this explains why for this map the coefficients were rational, the coefficients of Belly function. For this map, the coefficients of Belly function also were rational. And for these 5 maps, they belonged to a field of degree 5. Okay, here is the Belly function for the icosaedron, which was in fact found by Felix Klein in the 19th century. He looked for a rational function invariant under the symmetries of the symmetry group of the icosaedron. So what do we see here? We see, for example, in the numerator, all points are of degree 5. There is 0. X equal to 0 is a root of multiplicity 5. There are 10 more roots of multiplicity 5. So 11 points of multiplicity 5, which are black vertices of degree 5. And there is one more black vertex at infinity. Since you see here the degree is 55, and the degree of the denominator is 60. Okay? So, below in the denominator, we see 20 roots of multiplicity 3. They correspond to 20 triangles, which are the faces of the icosaedron. For f-1, we see, so the denominator is the same. We see how many? 20 plus 40, 60. 60 roots of multiplicity, 60. No, 30. 30, 10 plus 20. 30 roots of multiplicity 2. All of them are multiplicity 2. Here are roots of multiplicity 2, and here are roots of multiplicity 2. Also, we may note that the function depends on x to the power 5. All polynomials are polynomials in x power 5. What does it mean? It means that there is a rotational symmetry of order 5. So the function is invariant under this rotation. But not all symmetries are visible, there are many other ones, but okay, at least some of them are visible. Already this function gives some very funny phenomena. For polynomials, if a polynomial is a composition of several polynomials, then essentially this decomposition is unique. What does it mean? Essentially, there are only two cases when we can permute two polynomials when they commute. X to the power m to the power n is the same as x to the power n to the power m. And also Chebyshev polynomials commute, no other ones. But for rational functions, it is quite different. So this function can be decomposed as a composition of rational functions in many different ways. It is difficult to compute, but easy to draw. So if we quotient our map by the rotation order 5, we get this one. We will meet this map once again later. If we quotient this map by the quotient by symmetry of order 2, we get this one. And then here are 6. This map is of degree 6. So we get a segment, and so on. So we see the many possible decompositions of our rational function as this way. Okay. There are no commutation and so on. Well, maybe I may say it immediately. You remember that yesterday I made an operation with the icosahedron. I took the permutations sigma and alpha, which show the rotations of edges around black vertices and white vertices, and replaced one of these permutations with its square. I can make exactly the same operation with all these maps, everything which is drawn here, and so I get here something of a picture of genus 4, and then some pictures of genus 2, of genus 1, planar, and so on. So there are some very funny decompositions of certain meromorphic function which is covering of genus 4. Well, a particular case which is also interesting is the case of trees. A tree is a map which has only one face. So it is very natural to put there will be the only one single pole, and it is natural to put it at infinity. And then the rational function becomes a polynomial. These polynomials are called Shabbat polynomials. So for example, for this tree we get x to the power n. It is practically obvious that this tree is the inverse image of the segment 0, 1 under this polynomial. For the chain tree, we get the Chebyshev polynomial. Polynomials only the critical values instead of 0 and 1 become plus and minus 1. Here is another example. So, if we fix the only pole at infinity, then instead of fractional linear transformations, we have a liberty of only linear transformations, affine transformations. We can move this picture, we can make it bigger, and we can maybe turn it if we multiply by a complex constant, but the geometrical form remains fixed. So every plane tree has a canonical geometric form. It is not the most beautiful form, but there exists something which is canonical, which is attached to every tree. For maps, it is not that obvious because fractional linear transformation changes the geometry. But here, the geometry is fixed once and for all. The curvatures, the angles, the lengths, and so on can only be changed up to some homotopy and movement, parallel translations or something like that. Okay, just a few words about pre-images. So, if f is a rational function of degree n, and we take one point here, then usually we have n pre-images. They are just solutions of the equation f of x is equal to this fixed point y. If there are 2 points, which in order to distinguish between them we color black and white, we have n pre-images of the black point and n pre-images of the white point. They are just roots of the algebraic equation. So it is very natural. If we take a segment, usually we have n segments on the upper level and disjoint segments. If we take something else, we get n pre-images of this something else. Now, the situation starts to change if one of the points tends to a critical value. Its pre-images approach the corresponding critical point, a corresponding critical point. For example, if there is a pre-image of multiplicity 4, then these 4 pre-images tend to this one, and finally, when this black point comes to this one, the segments become attached to each other. The same thing happens with other forms. And so, when we have only 3 critical values, 0, 1, and infinity, we may consider the triangulation of the sphere. So here is a triangle. Maybe it is not it doesn't jump to the eyes, but it is a triangle because it has 3 edges, 0, 1, 1, infinity, and infinity 0. I denoted the vertices in 3 different manners: black, white, and a little star. Okay, the edges also, dashed edge, and okay, some other form. So there are 2 triangles, the upper half plane and the lower half plane. And then we take the inverse image, and every triangle is repeated n times. There are as many black triangles as there are as the degree of f, and as many white triangles as the degree of f. I show just a small part of the picture. So you see, every triangle has 3 vertices of 3 different types, 3 edges of 3 different types, and the colors alternate. Nothing bad, nothing nasty happens inside the triangles, since inside the triangles there are no critical values. Therefore, on the upper level there are no critical points inside the triangles. The only critical points are here, 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 and so on. Okay, so now I label the black triangles. I leave white triangles without labels. And then I understand that this picture gives a complete information about the covering, but there are some information which we don't need because we can recover it by a small part of the picture. So if we leave only this picture, then we can recover everything else. There is one single pole inside this face. There are edges like that, white and black triangles, and so on. And you see that the labels are now on the left bank of every edge if we go from black to white. And it seems that that's all. Yes, the next subject will be some problem about polynomials. Some problem which remained open for many years and which can be solved very easily by drawing pictures. That's all for today.
Would you make this computation for the example to work out? It seems that you assemble together all the roots of the same multiplicity in the polynomial instead of having factors. Is that important in the process of getting the answer?
Yes, it diminishes the number of variables and it simplifies the.
Yeah, that was it.
So in the canonical pictures for the Shabbat polynomials, they have edges.
Yes.
So can they change curvature of the side? The
No.
edge cannot change. It's
No.
bound in one direction or the
Yeah.
other.
Yes.
That's a theorem. That is easy to see this.
The only liberty is the multiplication by a complex number and adding a complex number.
But the inverse of an edge cannot do this.
You see, no, it is possible. It is complicated to get an example, but it is possible. There are how they call inflection points. Yes, there are some examples, but for many years people were unable to get such a picture.